Welcome everybody to our Lunch and Learn today. I like to say thank you to Klaus, who found our very good presenter, Diplom Mathematician Christian Alexander Graf at Agile Monday, and suggested to QA to run Lunch and Learn. And want to thank also my former project manager Holgi, who organized all this while I was in Beijing. And with this, I'd like just to hand over to Christian to tell us more about testing software strategies in Agile and non-Agile approaches.
Well, Harald, thank you very much, and welcome to Lunch and Learn about Agile and non-Agile testing, with a special emphasis on unit testing. First of all, just I would like to introduce myself. I'm not a friend of long curriculum vitae or something like that, so definitely that must do for a curriculum. So by trade, as you heard, I'm a mathematician. Originally, I still am, because I'm still giving lectures in mathematics at the University for Cooperative Education in Baden-Württemberg, Mannheim. In my other trade, I'm software tester since more than 10 years. And I also worked for some part of my life as a software developer, developing programs in Lisp and in C++ and some Visual Basic dialects. So that software ranged from enterprise resource planning software to programming algorithms for simulating stellar atmospheres in Heidelberg. Well, so if you have more questions or want to meet me in person, actually my office is not too far away from here, because I'm residing in the co-working space here in Nuremberg. So if you're in the mood talking to me, just pop in and we may have a cup of coffee. So that's where you find me. Well, first an overview of what you have to expect for this lunchtime. Nearly would have said concert. Okay, first of all, I want to give you a short outline and some short ideas at what quality actually means and what quality means in the context of software testing. Then we want to talk about about the relationship between developers and testers. What can developers learn from testers? What can testers maybe learn from developers? And then we will talk about what is actually testing, or what does testing in different software lifecycle models look like. So where you will find testing there, and what are the typical problems, and maybe the advantages of certain approaches. That we will discuss here as well, and I will present you an approach which goes back to Brian Marek and Lisa Crispin, which is the so-called Agile testing quadrants, where actually can decide where you would use a certain strategy for testing. And then we go in the end a little bit on good practices and major pitfalls when you start to introduce and to program unit tests. Okay. You may think not testing at all or doing just some debugging or so might have no effects, because software, nothing can really blow up. Well, if you think that, you're basically wrong, because things can blow up. What blew up here was the Ariane 5. And as I will show you later, or as we will discuss a little bit later, that could have been prevented by unit testing. You also could have prevented it by applying proper coding rules in every place of the software, by applying maybe code reviews. So there are different types of testing with which you can find such a thing. But things can blow up. And I think you wouldn't like to be the programmer who caused that line of code, because it was really a single line of code where you can trace that major failure back to. Okay, what is quality? Well, first of all, thinking about quality, well, it's something like you feel something. Sometimes it has also an emotional aspect, how you like something or not. However, that's hard to measure, and that's why there are some people who actually use their time sitting in committees and defining standards. They came up with some clever definitions, which I'm going to show you two of. First one is the general definition of what quality is, which is from ISO 9000. This is the degree to which a set of inherent characteristics fulfills requirements. Now, what the heck are inherent characteristics? We'll come to that later. And software quality is the degree to which a software product satisfies stated and implied needs when used under specified conditions. So the conditions are very, very important for the use of a software and whether you think it's quality or it's not of good quality. Well, but let's start with what you know from everyday life. What is actually quality in a project context? So classical project management, we have the following criteria. We have a certain scope that we want to deliver. We have a time until we have to deliver something, and we have a budget. The scope is how high you want to build a pyramid, with what kind of stones, what it should look like, things like that. Where's the quality? Where's the quality here? It's actually, should search for it a little bit. Well, if you do the things right, the quality is built in every step. It's constantly built in. So, what happens if you can't reach the scope? So, maybe you have not enough budget to buy enough stones to build such a pyramid. Well, actually, the Aztecs knew that built-in quality constantly is a good idea because this pyramid is still standing. And maybe you can see that there are people walking on it. So, what happens if you cut the time or the budget, or you have to reduce the scope? If you want to keep the scope, you have to add time and budget to reach whatever you wanted to reach. If you try to save some things in terms of quality, that means in some places you might just leave stones away. You might build parts from wood. What happens? After a few years, the wood would be rotten. The pyramid would crumble down. If you're building this thing, you also want that the steps built in here before are of good quality, because if you are working up there, you don't want to crush down. So building quality also means that you can rely on what others did or on what you did before. And that's a major fact in unit testing, as we will see a little bit later. Okay. So I have to build in quality in a constant way. But how do I know that quality remains a constant? For that, I have to measure it in some way. And for that, I need testing. And that's why Ron Jeffries, actually he's one of the developers and actually the inventor of extreme programming, states in software development, good feedback requires good testing. So testing is not only something that helps you develop good software for your customers, but it also gives you a feedback on whether the quality that you're delivering is still constant and still in the way you need it. Well, there are two major aspects of software quality. The one is something that you will build in. Take a look at the pyramid. We have here some architects that are built. Well, they do not really look like Aztecs, do they? Okay. You have your architects. They know how to build stones. They know how to put the stones together, that the building will not crumble. And that's actually what you should know also for software. You should know something about functional suitability, about the performance, how to program a system in order that you have good performance and efficiency, so that you have compatibility, usability. You may have your own ideas about what good usability is. Reliability, security, maintainability, and portability. Putting all these things together makes a good pyramid. However, this is not the way a user will experience quality. And that's why we have, actually this is a quality attribute model which comes from the ISO 25010, which is a norm about software quality. And there's a second model for quality attributes which states you have a quality in use. That's what actually the user experiences. And what the user here experiences, she can walk upstairs and downstairs on the pyramid without any worry. She can even talk with her mom on the phone while walking upstairs and downstairs, and she doesn't need to concentrate that she doesn't fall into any holes, gaps, or stumbles across something. So that's the customer's view. And here we have effectiveness, efficiency, satisfaction, freedom from risk, and context coverage. That's what you intend to use the software for now and maybe later on. Well, that you also have with SUSE Linux. You have certain parts of the software where you actually develop an enterprise server. But the use contexts of this enterprise server software are much different. One could be SAP systems, which are very, very, very complex things in themselves, in very, very different complex situations where the users will apply these systems. Or you have the Z system from IBM, which is, for example, used in contexts of financial institutes, large financial institutes like Deutsche Bank, for instance. The use contexts are quite different, but still you can rely on your development on the same view on quality, or at least that's what you try to do. So just introducing the concepts now. We'll come back to that later when we take a look into testing and the life cycle of a software. What that means. Oops. Okay, let's introduce a third view. We now have the user's view, we now have the company's view on quality. And now let's take a look at testing. Well, actually, testing is measuring the quality. We need good testing, as Ron Jeffrey says. And what are actually the typical views for developers towards testing, quality, and testers? It's a little bit archetypical. So, first of all, we have here the developer. This guy here. And he usually is really a curious person. He likes what he's doing. But when it comes to testing, he thinks, okay, he tests things. It means he tries out whether the things work usually as he expects it. There's no bad feeling about that. That's the way he just feels, or he just very often thinks. And of course, he wants the user, or the end user, his boss, his fellows, to be happy with the software he wrote. Now, let's take a look at the tester. He's a little bit more careful with the software. He knows that things can blow up. He's also curious and creative. He needs to be creative in breaking things. And he's very careful about whether this stuff works as expected. So he has his doubts. He should have his doubts. He should be a professional pessimist with that respect. And to that end, to make sure that his doubts come true or not, he tests thoroughly, systematically, and independently. So he doesn't try to take the same assumptions as the developer did when he wrote the code. Maybe not even the same assumptions as a requirements architect did. And of course, he likes to break things. He enjoys the big bang whenever he can trigger it, but that's not because he just finds destructivity in itself a goal, but because the user won't experience the crash then. Can help people with that. So, of course, for the developer, he often comes with bad news. Yeah. He did something awful to his baby. But nevertheless, developer and tester have a common goal, good quality. That's the common goal, and that's where they work together. The developer can give hints to the tester where changes have appeared. The tester can show the developer where he should take a good look. Now, if it comes to unit tests, we have here the problem that when you are writing software, you very often think in a constructive way. So you rather think of what should happen as in comparison to what can happen. That's a major difficulty. For instance, although I know what good tests should look like, when I write a program and write also the unit tests, and I take 2 days off and then take a look at the unit tests, I always find something, or very often I find something which I forgot. to implement in the unit test. So that's something that can easily happen when you're writing your own tests. Nevertheless, you should do it. Come back again to it later. So, come and go is good software. We have two perspectives, two psychological perspectives, the view of the developer, the constructive view, and the view of the tester, the more pessimistic, I would call it a little bit constructive, or maybe, what did they call it? Creative, destructive view. So, when and where do we test? Another approach. We are now in the life cycle of a software. Typical life cycle of a software is first you have a conceptual phase, that is when the idea for the software is born, and the software is then implemented within a project. Here you have the software project. Then a software is put into operation, and now naturally changes happen. This can be bug fixes, this can be service packs, this can be new releases, even new major releases. Still, it's basically the same software. And sooner or later, this is more or less at the customer side, a software may be retired, it's put out of operation. The data within the software still has a life on its own, might be migrated into other systems. And actually in all these phases, testing can happen. And one major problem for project managers or for general actually process management in companies is that if you take a look at so-called life cycle software development models, they only take care of, this part here, the requirements and the software project in itself. The changes are very often excluded. Which means also that when you budget a project, you don't think too much about how will be regression testing, for instance, done in later projects. Something that happens very often, or actually, it's a usual thing that happens. Well, the first of these models, described by Royce, was the waterfall model, where you start actually with the analysis and requirements phase, going to system design, implementation and coding. Then you have software testing as one phase, and maybe acceptance testing at the customer side, and then you put the thing into operation. So, very basic, rough process for implementing software, and not quite to the truth, because you always have, of course, iterations. You find bugs, maybe you need a redesign, and so on. It's not really reflected in the model, but at least you have phases where you can actually plan things with. Well, so software testing in the view of the waterfall model is actually a one-time activity. It's a final control if everything is according to specifications. So it reflects more or less what you would do in a factory when you produce goods there and do the final test on whether they meet your specifications or not. But actually, writing software is, to the most parts, a design process. So software quality management, software quality assurance should look a little bit different. It's not like you test something that always remains the same. Things change naturally when developing software. Well, let's also take a look at the economical aspects. Now with the waterfall model, because most representations of economical prospects are usually done funnily in like people who were working only with the waterfall. But nevertheless, in 2002, the National Institutes of Standards and Technology prepared a study to find out what is actually the state of quality management in software industries. And they found out that actually the annual costs of an inadequate infrastructure for software testing, resulting in defects in production and so on, is about $59.5 billion. And the possible savings would be around $22.2 billion. So there's some room for improvement. If you take a look at several studies where actually most costs arise of bad quality or costs of defects, you will find more or less curves like that. So the relative costs of defects per phase, where I would say actually the fixing costs for a defect found during requirements phase is actually our base value, our reference value. So when we come to design, it might double. When we come to coding, it might be 3 times that of requirements phase. When we are in the testing phase, it's usually double or even a little bit more than that of coding. If we come to user acceptance tests, it's even more. And when we find a defect in operation, the costs might be astronomical. For example, if you have to call back a car due to a software defect. Well, reasons for this are quite simple. The later the phase, the more people are involved, and the more process steps you have to rerun. So this problem here is not only a problem of costs, but it's also a problem of time to market. Because the later you find a defect, the more steps you have to do, the more costly it is, but also you can't do other things in that time when you have to fix the bug and redo things. Anything that you need to redo takes time away from things you could have done in another way, or other things that you could have implemented. So finding bugs saves time and money. Finding bugs early. And that's actually the second principle for testing that I would like to establish today. The first one was write good tests so that you know where you are. The second one is start testing activities as early as possible. And this idea was implemented in the so-called V model, or the generic V model. It's very often used for development of medical devices, for development of software for pharmaceutical delivery, construction, production, and so on. So basically, it first looks like more or less like the waterfall model, only it's a little bit more elaborate. We have first a phase in which we have user requirements, then we get a functional specification out of the user requirements, a design specification, a unit specification, and then we go to coding, and then we have unit testing, integration testing, system testing, and acceptance testing. Okay, more or less, this looks at first glance like a waterfall that we just twisted in the middle. But it's more than that, because the V model states start testing activities with the corresponding design activity. So testing is actually here put into different phases, usually called testing levels. And each testing level corresponds to a certain design phase. So as soon as you have the user requirements ready, you should at least review them, and you should find out if they are testable. Same goes for functional specifications. So actually, if you have the system architecture, it's functional specification, design specification, you may need a very elaborate testing system for testing a large system. So you start already here to specify what a testing system should look like. Things like that. So I don't want to go into more details here. We could have a own talk on this problem of test management. Okay. And it also, the different testing levels also take into account that you have actually a difference in what the user experiences and what you necessarily, as a vendor of software, have to define as quality. So the lower testing levels test more or less your product quality attributes, whereas in the higher testing levels, you should go more towards actually what the user expects. Well, last but not least, we have Agile models. As a prototype, I would like to name here Scrum, where actually we try to reap the benefits of all the models and do things fast. You know, actually a drawback, if I go back to the waterfall model, is of course, if you find out here, actually, during dynamic testing, that you need to change something here, which is a little bit late, then again you have to draw back from the waterfall model, that you actually have to do a lot of rework. So there are several models actually then which treat software as something where we would like to buy prototypes and so on, so that an end user can see at an early stage what he will get in the end. Okay. Again, also with Scrum, we start with some requirements, with some kind of requirement phase. We have something which is called a backlog, a product backlog, and we have a product owner who's actually the master of this product backlog. He's the one who must say which are the most critical components from a business point of view, which are the most important components from a business point of view. And then he presents this backlog to a team of developers, or maybe to several teams, depending on the size of the organization. And they decide what they are going to implement first, based actually on the prioritization done by the product owner. Okay, and that's what they decide to implement first. They put into a so-called sprint. That is usually a time-boxed period of time, typically between 1 to 4 weeks, might be longer. Sometimes embedded branches usually have 6 weeks because, you have to deal often with new hardware and so on. Okay, so this is actually adaptable like you want. And this sprint is planned by the team, asking questions to the product owner. And actually the master for this all, or the one who supports the team in keeping a process, a good Scrum process, removing impediments, keeping trouble away from the team, that's actually the job of the Scrum Master. He might be a member of the team, but not necessarily. So what they do is they decide what they're going to implement within, let's say, 4 weeks. And they also take, during this time, already a look at what is coming towards them for the next sprint. It's called a backlog grooming. However, the goal is to, in this fixed period of time, to achieve a potentially shippable product. That's the basic idea of Scrum. And of course, they have daily meetings where they check how they proceed. Well, how's testing implemented here? Built in, directly in the process. During the sprint planning, you already have to think about how you're going to test things. There are different approaches to do that. Some teams define testing tasks. Others define the tasks for testing in a so-called team charter. So that when they do a story or when they implement a user story, they already know what are the typical things for testing they have to do. Depends on the training of the team, depends sometimes on the software and what they're going to do. Depends also to how complex the testing might be, how you do that. And the actual testing is done during the sprint. You test new features, and this is the most important part. Since every sprint you will add things, you must make sure that the old things are still working. And that's why I need a great deal of regression testing. Because else, implementing new things, you always run into old bugs. So you won't proceed with what you actually want to implement. And that's why you should, when you're doing Scrum, start doing proper testing, and in a way that you can do regression tests right from the start. Because else your teams will not be fast. They will be stuck up with the old Merc. Okay, and another problem, or another, let's say, a challenge is that within a sprint you don't have testing phases anymore, test levels like in the V model. So potentially you need to test on all levels at the same time. This can be done, but it takes a little bit of experience and introduction of proper tools and so on. Okay, let's talk about different test approaches and types. We have already seen that we can test on several levels. In the Agile world, this is represented by testing quadrants. Don't mistake me, it's not the same as testing levels. It's just another way to look at tests that you could do. Okay, what do we put into these quadrants? Well, first of all, we have here a large square. And on each of the faces of this square, we are going now to write something. And on the first square, we say, okay, this is business facing. So in the upper two quadrants, we will put all testing approaches that actually are testing something which has to do with the business, with what customers expect. On this phase, we put something that's called critic product. And that states actually, here we want really to break things in a creative way. We want to critique the product, what is going, what is not working. Then we have here a phase that says support a team. Okay, you might have asked yourself, why is here a climber up there? Supporting the team is actually testing that tells you when your software is broken, when you can't go on with the proper speed, when you can't climb on in the same way. So tests of this kind also are kind of a safety rope on that you should always rely. If you can't rely on that, climbing can be very dangerous. And the last one is technology facing. It's toward your technological quality attributes, like for instance performance. So here you test actually the technology that you're using, which is very important for server business. So many of your tests will be, I assume, technology facing. And then we have the corners. And they will also put something. In the corners we have tests that are here, automated and manual. For critic, product and business facing, there are a set of manual tests. Then we have here a corner which says tools, which is usually more or less than technology facing tools. And we have automated tests. Okay. So in this quadrant we would put testing approaches which would be supporting the team and would be business facing. Example. Testing user stories. One thing, did you understand the user story properly? You test it, then you guess, is this working? How would a user understand this? Okay, I'd better ask the product owner what that means. I once did a project with a company who called actually this feature understanding testing. Or actually they put something here which was called feature understanding testing, which was quite near to testing user stories. I like this term very much because it expresses actually very good what they were doing. It was supporting the team in understanding the features, and it was business facing. So they started to understand the business better too. Prototypes and simulations. It's business facing. Is this what we can get in the end? And it's supporting the team to understand the technology with which you're working. That I have this example here. This is, for example, a prototype or simulation that would be shown to a user. You might have other prototypes and simulations that I personally would put down here if they are just to try out a new technology. So what's written here is not written in stone. It depends on what you are testing. Testing is always context dependent. So it might be well down here. Okay, let's find an example for manual testing, which is business facing and also critiquing the product. So for example, user acceptance testing. Really putting in the user's view and see what is working, what the user expects and what not. Might be even done by users or might be done by technical support who probably knows best what the users are doing with the software. Then we have the so-called exploratory testing, which is actually trying things out not ad hoc, but in a planned and actually systematic way. One could give an own talk on exploratory testing. It's a very powerful tool if you're an experienced tester. And we have usability testing from the user's point of view. Then for critic product, we also have, which is heavily tool-based, performance testing, testing for reliability, and so on. This is also called typical ility testing. So because you have reliability, usability, maintainability, and so on, all the ilities, except for usability, that's usually up here. Okay, now, first things last, so unit tests. Unit testing is usually here. When you're testing units, when you're testing components, when you're testing a method of a class, usually do not test something directly that the user will experience. It's maybe a small step a user will do in a larger process or in a larger business process. So unit testing is on the one hand automated because once you have the unit tests, you can run them in an automated way. You don't need to click something. They usually also already with the modern environments run with the build. And they support a team. They support you as a programmer because whenever you change something, you run the unit tests and see if you broke something on the way of changing it. Okay. Also, we have here things like dynamic analysis, which is technology facing, and supporting the team to see whether actually so-called non-functional requirements for your software are met, for your software component, for instance. Now let's go into unit testing a little bit more. Well, testing early means covering product risks early. Testing early we can already achieve by doing reviews on requirements, on specifications, on the system architecture, and so on. When it comes to coding, the earliest point is when we test is actually when we write the code. We can also directly write unit tests. And these unit tests here, they are the safety rope that enable us to change things without breaking something. And if you write unit tests, you need actually to take more the approach also of a tester. You take also a tester's view on your own code, and it broadens your the view you have on your source code. Okay, let's talk about what should you implement. One problem is to achieve coverage. Did I test enough? Have I written enough in my unit test case? Or did I write too much? One thing you can use is actually systematic testing approaches. 2 examples. The first one is the so-called equivalence partitioning, a very easy method. We actually take a look at what the software should do. Usually different input domains are treated in a different way. You can't test everything, you can't test every value. So you take a look just at which input domains are treated in this, or which parts of the total input domain are treated in the same way. And for that you write a unit test. If an input domain is treated another way, you write a second unit test. So if you take a look at these triangles here, we have here a non-isosceles triangle, we have here an isosceles triangle, here we have a non-equilateral triangle, and here we have a more or less equilateral. It should have been an equilateral triangle, I think. If you look closely, it is not. Okay. The way we could do an equivalence partitioning here is actually first, okay, equilateral triangle would be one input domain. An isosceles triangle would be a second input domain, and a non-equilateral triangle would be a third input domain. But there's a fourth input domain. Somebody might put in or might try to enter something which is no triangle at all. So a minimum number of test cases would be here 4 test cases. I put in here some Java unit tests in here. And so here actually the first one reads test no triangle, test isosceles, test equilateral, test non-isosceles. And here we can learn something too about unit tests. Is this the way you would implement these tests? What could you do better? Actually, it's quite easy. Because if you take a look here, and here, and here, and here, you basically have the same code. That's something you don't do. So for these types of things, you would just write a wrapper. Because when the interface for input or output changes, you would have to rewrite these 4 areas here, which is too much trouble. This is not very maintainable. You have basically copy and paste code here. No good idea. So this is what you would do here when you started to write a test like this. As soon as you write a second one, you should refactor your code. So it means to write a wrapper for this, that you have an own class, which you just put here, which makes basically the test with these input values. Also, another clean code principle is you should have readable names. Try is a very nice word game for triangle. But maybe it would be better to call that test triangle, because then it's clear what it means. There's a very nice book by Robert C. Martin, which is called Clean Code, and you will find a lot of stuff on such programming rules. Also about writing good unit tests in there. Although the examples are all in Java, but you might live with that. Okay. Another very easy method are boundary values. Because typical programming mistakes are, I want to write a smaller or equal, and I write just a smaller typo. I misread the specifications with respect to that. Or I'm in a new programming language and inexperienced with accessors to lists. So I point not to the end of the list, but just one behind. So these are typical boundary values. And if you take a look into the definition of boundary value analysis and appropriate standards, you see actually not only if you have a defined domain of input, not only the value directly at the domain boundary, but one increment to the left and one increment to the right are defined as boundary values. So these are typical values that you can test. And also, if you take a look at the data type, the boundaries of the data type itself could be boundary values. If you consider this, you might just have prevented this. This was Ariane 5. The source code for Ariane 5 used some parts of the source code of the rocket ship that came before, Ariane 4. And in that source code, actually, there was a coercion from a floating point value to a short. For horizontal velocity, there was a check whether actually you had an overflow, but not for vertical velocity. That was omitted. And since in Ariane 4 that hadn't been a problem, but with Ariane 5, which was just a little bit faster, at a certain point in climbing, this gave rise to a problem because there were now negative values with which the system had to deal. And so the navigational system switched on the reserve system, which ran with the same software. Basically the same error occurred. And then it tried to, you can see that here, it came off course here. Tried to actually correct the course, and then the ship became critical unstable and self-destructed. That's what you can see here. It's a single line of code that caused this error. Could have been found by code review, by a simple unit test. Even equivalence partitioning with taking into account invalid values, input values, could have done this. Or boundary value analysis. Well, some further design techniques. So some things for reading. Black box methods like so-called decision table testing, when you have complex logic. State transition testing, when you basically can, or when your specifications are basically like a state machine. If your software is described like a state machine. Syntax testing, a very good thing for testing parsers, regular expressions, and so on. Or white box methods. Did we cover everything in the source code itself, like statement coverage, branch coverage, or certain condition coverage measures? And if you want to look these up, you can find them in a British standard, which is downloaded for free, because the funny thing here is the group that developed this standard put actually the final draft under a common license. And this you can download from here. It has a lot of examples in the appendices. So it makes a good reading if you want to learn something about testing methodology. Okay, other things that you can use are checklists for fault attacks. There's a book by James Whittaker, about such fault attacks. Checklists help to great extent when you, in any case, just one example. You add something like a trace routine to your program, which writes a log into a file. And the specification is, Once the file has reached a certain size, a second file should be opened. A typical fault in this situation is the second file is never opened, but the first file is overwritten. Or another one is the second file is tried to be opened with the same name. Now already a file exists. And the program just stops there. So such things you will find in checklists, typical fault attacks. You also can include them or use them for your unit tests. Taking a look at such things gives you just more experience what you can check or what you should check for. Okay. You will very often hear about, in the context of unit tests, about test-driven development. And the approach is to gain a good coverage of your requirements, of your user stories. That's the idea behind it. And in Robert C. Martin's book, you will find actually 3 laws how to write test-driven use case or test-driven unit test cases. The idea is, before you write a single line of code, you first implement unit tests according to the following laws. You may not write production code until you have written a failing unit test. Now you could be carried away by starting to write unit tests, especially if you are a tester. Nevertheless, that's what you shouldn't do. The second law is you may not write more of a unit test than is sufficient to fail, and not compiling is failing. So you need to compile things, and you do not write more unit tests than you actually need to implement your first lines of code. The third law, you may not write more production code than is sufficient to pass the currently failing tests. So once your tests are actually a pass, you stop and write the next unit tests. This is a completely different completely different approach in implementing software. It's really hard to do that at the beginning. It's still hard for me. And it takes time, it takes exercise, it takes practice to do that. You don't know that right, or you can't do that right from the start. And that's why actually Dave Thomas developed a concept for practicing that, a so-called concept of coding katas. And it's described on his webpage, codecutter.com. I could give an own talk on that. I wouldn't do that because I'm not really a proficient code cutter performer. There are people who really can do that in a marvelous way. So, but if you're interested in the concept, here is the webpage. I can only give you an overview, and that's my goal actually. So take a look at that. There's a lot of stuff here in the presentation which you can take a look at later on. Just a teaser. Well, there's another thing you should take into account when you're doing the test-driven development, when you use the test-first principle, because it usually won't work if you don't use XP practices. And XP practices were developed by Ron Jeffreys, and I can only recommend his webpage, because there you will find a lot of information on how XP should be done, can be done. I just want to show you the connections between the basic or the XP practices and test-driven development, which is important for unit testing. First of all, you need to make sure that your unit tests are maintainable. Because if they are not maintainable, when you add code, you will surely abstain from changing your unit tests because you won't understand them maybe anymore. They might even break if they're not maintainable, not run anymore. So sooner or later, if you do not have maintainable unit tests, you will stop from evolving them. And as Robert C. Martin says, that's worse than having no unit tests at all. Because you live with a false concept of safety and security about change code. So, you need to make sure that your tests are maintainable and also that your code is maintainable. And that means that you need coding standards. Keep it simple and smart, the KISS principle. And applying coding standards and keeping things simple and smart means that you need to refactor when things become complicated. A few slides ago, you've seen an example for that. In 4 unit tests, the same code, which was merely basically more or less copy and paste, only with a few different numbers. That's not simple and smart. There you apply refactoring then. The second point is you need to know about the methods, so that you don't miss something, that you really have enough unit tests, that you know which unit tests to write. And that means you need some people in your team who know how to test, who know systematic testing procedures. And you might apply pair programming, putting people together which are experienced in testing and which are maybe more experienced in a certain programming language or with a certain technique in which, or with certain kind of features, set of features. Actually, this was the way in which JUnit was developed. Because two programmers sat together in a plane. One wanted to learn Java, the other wanted to learn about actually the unit test suites the other had developed. And so they sat together and started to develop JUnit. You can read it in the book from Robert C. Martin. The next point is, you need to know what to test. You need to know what your requirements are. Sometimes this is not so specific. You need to find the proper test objectives. That means you need somebody who knows what a customer will expect on site, a person that you can ask, which can describe it in a way to you, maybe in a metaphorical way that you understand if you do not know well the context. And you need to be able to execute the tests. So that means you need something like a continuous integration environment. Building the software, building your system and running the tests at the same time. And these things must become feasible. You must be able to do this. So that means, first of all, collective ownership. There's no line of source code that belongs to a certain developer because he knows best. Everybody is in principle allowed to change the code. Usually will talk to each other. You will take the most experienced person to change something, but nevertheless, you need collective ownership. The second is, you can't do everything within 4 weeks, so you must decide on what you are going to do. Next, first, second time, and so on. You need to find a sustainable pace. Which means also that you need small releases. If you do big releases, you might lose the overview in what you're doing. And so that you can decide on your own what is for you or your team a sustainable pace and what should go into a small release, you need a planning game. And here you see that you have here in extreme programming quite a lot of ideas which you also have in Scrum. So actually this part is making it feasible, is actually the part that went into Scrum. But if you really want to work properly with Scrum in software development, you should think about applying the other things too. Well, how to apply the tester and the developer here? In modern teams, you do not only have developers and development teams. You also have testers in the team. And since in Scrum, product owners are sometimes hard to get, very often the tester replaces the product owner to a certain extent. So he's the one who must know or must understand what the product owner maybe wants most. And he can also be a valuable ally when it comes to implementing unit tests. For example, in terms of pair programming, sitting together and thinking about how to implement a test, what should be implemented as a test. I don't know if this is cheese. Some pitfalls. Things you always should consider. Some things up now. Do your tests cover the functionality? With TDD, they will probably do, unless you forgot something to implement. And, very important thing, invalid or unexpected input conditions. Sometimes even masters in coding katas forgot these. I once saw a very good coding kata conversion from Roman to Arabic numbers. And the clean syntax test, or actually the developer showing the code on kata, actually keyed in a perfect, clean syntax test that was really according to British standard, although that person never heard about a British standard. What he forgot were the dirty syntax tests. So always remember invalid or unexpected input conditions. And these are the ones that can really give trouble in the field. Things you didn't think about. And this is where the tester can help. Are your tests maintained? Are they up to date? Or are they more or less legacy, icky stuff? Are they maintainable so that they do not become icky stuff? And do you run your unit tests? It's nice of having them around, but do you run them? And always be aware that unit tests do not cover everything. There are some things you can't do with unit tests. There are a lot of things you can do, but not everything. So always think about what can you do at a component at a unit test level. What do you need to cover with other tests, maybe on later stages? Okay. Put things into a nutshell. Good practices. Use systematic test design. Pair with testers or other developers. For I see more than 2. Make sure that your unit tests remain maintainable, that they are not legacy, that is not really usable. So, review them from time to time. And also consider using test-driven development. But remember, it takes time to learn that. Last but not least, start with small steps, but start.